Picture a world where the oceans stretch endlessly, where life evolves at a pace that makes Earth's history seem slow motion. Now imagine this isn't science fiction, it's real, and it's happening right now on a distant exoplanet. Scientists have uncovered Exoplanet X, a waterworld so alien yet so familiar, where evolution races ahead in ways we're only beginning to understand. What if this planet holds the key to life's greatest mysteries? What if its oceans hide answers to questions we haven't even thought to ask? This isn't just another exoplanet. It's a living laboratory, a place where the rules of biology might be rewritten. By the time we're done, you'll see why this discovery could change everything we know about life in the universe. Stay with us, because what lies beneath those alien waves will challenge what you thought was possible. Now let's dive into how this extraordinary world was found. The discovery of Exoplanet X wasn't just luck. It was the result of cutting-edge technology and relentless curiosity. Astronomers first spotted it using a combination of two powerful methods. The first, called transit photometry, involves watching for tiny dips in a star's brightness as a planet passes in front of it. The second, known as radial velocity, measures the subtle wobble of a star caused by the gravitational pull of an orbiting planet. Together, these techniques painted a clear picture of something remarkable lurking in the data. The breakthrough came thanks to instruments like the James Webb Space Telescope and ground-based observatories equipped with ultra-sensitive spectrographs. These tools didn't just detect Exoplanet X, they revealed its potential. The planet orbits snugly within the habitable zone of its star, a region where temperatures could allow liquid water to exist. But what really sent shockwaves through the scientific community was the sheer abundance of water. Initial estimates suggested a global ocean with no land in sight, a scenario that defied expectations. When the findings were published, reactions ranged from excitement to skepticism. Some researchers questioned whether such a world could even exist, while others saw it as a game-changer for astrobiology. One thing was certain: Exoplanet X wasn't just another distant rock. It was a beacon, hinting at the incredible diversity of planets and life that might be waiting in the cosmos. And with every new observation, the mystery only deepens. Now let's turn our attention to the star at the heart of this cosmic mystery. Exoplanet X orbits a red dwarf, a type of star far smaller and cooler than our Sun. While our Sun burns bright with surface temperatures around 5,500 degrees Celsius, this red dwarf barely reaches 3,000 degrees, glowing with a dimmer, reddish hue. But don't let its modest size fool you. This star is a powerhouse when it comes to longevity. Red dwarfs live for trillions of years, far outlasting the 10 billion-year lifespan of stars like our Sun. That means Exoplanet X has had an unimaginably long time for life to emerge and evolve under its faint light. The star's small size also creates a unique dynamic with its orbiting planet. Because the habitable zone is much closer to a red dwarf, Exoplanet X circles its star in just 20 Earth days. This tight orbit subjects the planet to intense tidal forces, likely locking one side in perpetual daylight and the other in endless night. But here's the twist: that very closeness might be the key to its watery abundance. Unlike Earth, which formed in the warmer inner solar system, Exoplanet X could have started as an icy world farther out, migrating inward over time and melting into the ocean-covered gem we see today. Comparing this system to our own raises fascinating questions. Our Sun's steady energy allowed life on Earth to flourish in sunlight, but Exoplanet X's dim star forces life to adapt to a twilight existence. Could photosynthesis even work here, or would organisms rely on chemical energy from hydrothermal vents? The answers might rewrite what we know about life's possibilities. One thing's certain: this tiny star and its oceanic companion are challenging every assumption about where and how life can thrive. Now, let's plunge into the depths of Exoplanet X itself, a world where land is nothing more than a distant memory. Picture a planet where the ocean stretches endlessly, covering nearly 100% of its surface. No continents, no islands, just an unbroken expanse of water deeper than anything we've seen in our own solar system. This isn't just a water world, it's a global ocean with mysteries lurking beneath every wave. So how did this planet become such an aquatic paradise? One leading theory suggests Exoplanet X started its life much farther from its star, in the cold outer reaches of its system. There, it would have formed as an icy body, a massive snowball made of water and other frozen compounds. Over time, gravitational interactions or the pull of other planets could have nudged it inward, into the warmer habitable zone. As it migrated closer to its star, the ice melted, transforming the planet into the liquid-dominated world we observe today. Another possibility is that Exoplanet X formed from icy planetesimals, small building blocks rich in water, that collided and stuck together. Unlike Earth, which gathered drier materials in the inner solar system, this planet's birthplace was a water-rich environment, setting the stage for its ocean-covered fate. But here's the puzzle. Why didn't it grow into a gas giant like Neptune or Uranus? The answer might lie in its formation timeline. If Exoplanet X accumulated its water quickly but didn't capture enough hydrogen and helium before the star's solar wind blew them away, it could have ended up with a massive ocean instead of a thick, gaseous envelope. What's truly remarkable is how this planet defies expectations. Most worlds with this much water would either freeze solid or become steamy, inhospitable greenhouses. Yet Exoplanet X strikes a delicate balance, its thick atmosphere trapping just enough heat to keep the ocean liquid, while its distance from the star prevents a runaway greenhouse effect. It's a reminder that the universe loves to surprise us, and that the rules for building a habitable world might be far more flexible than we ever imagined. Now, let's rise above the waves and take a closer look at the sky of Exoplanet X, because its atmosphere is just as fascinating as its endless ocean. Unlike Earth's thin, breathable layer, this planet is wrapped in a dense, swirling blanket of gases that play a crucial role in shaping its environment. Scientists analyzing light passing through its atmosphere have detected some intriguing ingredients. Oxygen and methane stand out, two gases that, when found together, often spark excitement because they can hint at biological activity. On Earth, these gases are largely produced by life, from plants releasing oxygen to microbes generating methane. But here's the twist: Exoplanet X's oxygen might not come from photosynthesis. Without sunlight penetrating far below the ocean's surface, alternative processes like water molecules splitting under intense radiation could be at work. Meanwhile, methane might bubble up from hydrothermal vents, feeding ecosystems we can only imagine. What's truly remarkable is how this thick atmosphere acts like a planetary thermostat. It traps heat efficiently, preventing the ocean from freezing into a solid block of ice despite the planet's distance from its star. At the same time, it shields the surface from harmful cosmic rays and stellar winds, creating a stable if alien environment. Think of it as a natural force field, one that balances warmth and protection so precisely that liquid water can persist across the entire planet. But how does it avoid becoming a runaway greenhouse like Venus? The answer lies in its composition. While exoplanet X's atmosphere is dense, it lacks the overwhelming amounts of carbon dioxide that turn planets into scorching wastelands. Instead, a mix of nitrogen, water vapor, and trace gases creates a milder greenhouse effect, just enough to keep the global ocean from freezing, but not so much that it boils away. This delicate equilibrium raises another tantalizing question. Could such an atmosphere also nurture life? With protection from radiation and steady temperatures, the stage is set for chemistry to become biology. And as we'll see next, the ocean below might already be teeming with possibilities. Now, let's dive into the invisible forces shaping exoplanet X, because its dance with its star is anything but ordinary. The planet's close orbit and likely tidal locking mean it's constantly stretched and squeezed by gravitational forces, creating a world where the ocean never sits still. Imagine the star's pull acting like a cosmic hand, gripping the planet so tightly that one side always faces the light while the other remains in eternal darkness. This tidal locking doesn't just create a permanent day and night side, it generates immense friction within the planet itself. That friction heats the interior, fueling volcanic activity on the seafloor and churning the ocean with currents far more powerful than Earth's Gulf Stream. These tides don't just move water, they reshape the planet. The relentless push and pull likely trigger underwater earthquakes and eruptions, cracking the seafloor open to release minerals and warmth. Hydrothermal vents, much like Earth's black smokers, could dot these fissures, spewing nutrient-rich plumes that become oases for life. But here, the scale is staggering. Vents might stretch for miles, powered by energy we'd struggle to replicate on Earth. What's even wilder, the star's gravity might warp the planet's very shape, subtly flattening it at the poles and bulging at the equator. Over time, this distortion could funnel ocean currents into planet-wide whirlpools, mixing warm and cold waters in ways that distribute heat and perhaps life across the globe. Yet this delicate balance comes with risks. If exoplanet X drifted even slightly closer to its star, the tides could grow so extreme that they rip the ocean apart, vaporizing water into space. For now, though, it orbits in a sweet spot where chaos and stability collide to create a world unlike any other. And as we'll soon see, its depths hold secrets that defy even our wildest imaginations. Now, let's plunge into the abyss of exoplanet X's ocean, a realm so deep it makes Earth's Mariana Trench look like a puddle. Scientists estimate this global ocean could stretch hundreds of kilometers downward, a crushing, lightless world where pressure builds to thousands of times what we experience on land. At these depths, the rules of life as we know them bend. The weight of all that water creates pressures so intense they would flatten a submarine like a soda can. Yet this extreme environment might be teeming with organisms built to withstand the squeeze. On Earth, we found microbes thriving near hydrothermal vents under similar conditions, but here, the scale is unimaginably larger. The ocean's staggering depth also means layers upon layers of distinct habitats. Near the surface, where sunlight might barely penetrate, photosynthetic life could cling to existence, but dive deeper, and you enter a realm of perpetual darkness, where creatures might rely on chemosynthesis, drawing energy from chemical reactions, not sunlight. Pressure isn't the only challenge. The sheer volume of water could create slow, colossal currents, transporting heat and nutrients across the planet over centuries. These movements might connect distant ecosystems, allowing life to spread in ways we've never seen. And then there's the mystery of what lies at the very bottom. Some theories suggest exotic forms of ice, like hot ice, could form under these extreme pressures, creating a bizarre, slushy seafloor. Others speculate about vast networks of underwater caves, shielded from the chaos above, where life could evolve in isolation. One thing's certain: Exoplanet X's ocean isn't just water. It's an alien laboratory where depth and pressure rewrite the possibilities of biology. And as we'll soon discover, the life that calls these depths home could be stranger than anything we've dreamed up. Now, let's turn our attention to the fiery underworld of Exoplanet X, its hydrothermal vent systems. These deep-sea chimneys, spewing superheated water and minerals, could be the beating heart of life on this alien world. On Earth, hydrothermal vents are oases in the abyss, supporting entire ecosystems that thrive without sunlight. But here, the scale and chemistry might be unlike anything we've ever seen. Imagine vents towering like skyscrapers, their plumes rich with compounds we'd consider toxic. Yet in this extreme environment, such chemicals could be the foundation of life. Instead of relying on photosynthesis, organisms here might harness energy through chemosynthesis, converting sulfur, methane, or even hydrogen into fuel. It's a process we've glimpsed in Earth's deepest vents, but on Exoplanet X, the sheer abundance of these energy sources could supercharge evolution. The planet's intense tidal forces likely keep these vents hyperactive, constantly churning out nutrients. This non-stop buffet could support sprawling communities of life, from microbes to larger, more complex creatures. Picture tube-like organisms anchored to vent walls, or free-floating predators adapted to hunt in the scalding currents. And there's another twist. The chemistry of these vents might be far stranger than Earth's. With higher pressures and different minerals dissolved in the ocean, the reactions could produce exotic compounds, materials that could reshape our understanding of biochemistry. Some scientists even speculate about life forms built around silicon instead of carbon, thriving in conditions that would obliterate Earth-like organisms. What's clear is this: hydrothermal vents on Exoplanet X aren't just geological features, they're potential cradles of life, rewriting the rules of where and how biology can exist. And as we'll see next, the creatures that call these vents home could defy even our wildest imaginations. Now, let's dive into the extraordinary possibilities of life on Exoplanet X. Given its extreme conditions, crushing pressures, perpetual darkness, and scalding vent systems, the organisms here could be unlike anything we've encountered. Start with the smallest inhabitants, microbial extremophiles, similar to Earth's deep-sea bacteria, might dominate the vents, thriving on chemosynthesis. But here's where it gets fascinating. The sheer abundance of energy and unique chemistry could push evolution toward more complex forms. Picture creatures with gelatinous, pressure-resistant bodies, their cells reinforced to withstand forces that would crush Earth's deep-sea life. Some might resemble the translucent jellies of our oceans, but with adaptations like bioluminescent lures to navigate the eternal night. Others could evolve rigid, heat-resistant exoskeletons, clinging to vent chimneys like alien crustaceans. Then there's the question of mobility. In a world without sunlight, predators might rely on sensing vibrations or chemical trails to hunt. Imagine serpentine organisms weaving through hydrothermal plumes, or filter feeders anchored to currents, their tendrils sifting minerals from the water. Earth's anglerfish offers a clue here. Similar creatures could use bioluminescence not just to attract prey, but to communicate or even camouflage in the glow of vent fluids. And let's not forget symbiosis. On Earth, vent ecosystems thrive on partnerships, like tube worms hosting bacteria in their tissues. On exoplanet X, these relationships could be even more intricate. Perhaps larger organisms harbor entire communities of microbes inside them, trading nutrients in a high-stakes dance of survival, the most tantalizing possibility. Life here might not even rely on DNA. Alternative biochemistries, like silicon-based structures, could flourish in this alien ocean, creating organisms that challenge our very definition of life. While Earth's deep sea offers glimpses of what's possible, exoplanet X could rewrite the book entirely. As we ponder these wonders, one thing becomes clear. The next frontier isn't just about finding life, it's about discovering how wildly inventive it can be. And that leads us to an even bigger question. Why did evolution here seem to sprint ahead of Earth's? That's a mystery we'll tackle next. Now, let's unravel the mystery behind exoplanet X's accelerated evolution. What could have pushed life on this ocean world to evolve at such a breakneck pace compared to Earth? One compelling theory points to its shorter orbital period. Exoplanet X completes a full trip around its star in just a fraction of the time Earth takes, meaning its years, and by extension, its generations fly by much faster. More generations in less time could mean more opportunities for mutations and adaptations to take hold, speeding up the evolutionary clock. Another factor might be the intense radiation bathing the planet. Without a thick ozone layer like Earth's, high-energy particles from its star could bombard the surface, increasing mutation rates in organisms. While this would be deadly for most life as we know it, extremophiles on exoplanet X might have turned this challenge into an advantage. More mutations could lead to faster genetic diversity, giving evolution more raw material to work with. Then there's the planet's volatile environment. Unlike Earth's relatively stable oceans, exoplanet X's tides and currents could be in constant flux due to its tidal locking and proximity to its star. Rapid shifts in temperature, chemistry, or even vent activity might force life to adapt quickly or die out. In this pressure cooker of change, only the most flexible species would survive, and those that do could evolve startling new traits in record time. Some scientists even speculate that life here might have gotten a head start. If exoplanet X's global ocean formed earlier than Earth's, or if its chemistry was primed for complexity from the beginning, life could have had millions of extra years to experiment and diversify. Combine that with all the other factors, and you've got a recipe for evolution on fast forward. So, while Earth took its time crafting the diversity we see today, exoplanet X might have sprinted ahead by turning adversity into opportunity. But what does that mean for the life forms calling this world home? That's a story written in bioluminescence and survival, one we'll explore next. Now, picture this: a world where the ocean's darkness is pierced by swirling constellations of living light. On exoplanet X, where sunlight barely penetrates the crushing depths, life might have turned to bioluminescence as its primary language, a dazzling dance of survival and communication. Unlike Earth's deep-sea creatures, which use light sparingly, like the angelfish's glowing lure here, entire ecosystems could pulse and shimmer in synchronized displays. Imagine schools of alien organisms flashing like underwater auroras. Their bodies evolved to emit light in patterns we've never seen. On our planet, bioluminescence often serves singular purposes, attracting prey, signaling mates, or confusing predators. But on exoplanet X, with its faster evolutionary clock, life could have taken this adaptation to extraordinary extremes. Picture symbiotic relationships where microbes coat larger creatures, turning them into living lanterns. Or predators whose entire bodies act as lures, mimicking the light shows of their prey to ambush them. The ocean's perpetual night might have given rise to a visual language as complex as any on land, with colors and flashes conveying messages we can only guess at. And let's not forget the sheer scale. Earth's deepest trenches host flickers of light in isolated pockets, but Exoplanet X's global ocean could be a continuous galaxy of bioluminescence. From its abyssal plains to its hydrothermal vents, every corner might glow with activity, a testament to life's ingenuity in the dark. If evolution here truly outpaced Earth, these light-based ecosystems could be far more advanced, turning the planet's waters into a living light show unlike anything in our solar system. So, while Earth's deep-sea creatures offer glimpses of this phenomenon, Exoplanet X might have transformed it into an art form. But what happens when these glowing organisms interact? That's where the real drama begins, a story of predator and prey, written in flashes and shadows. Now, let's dive deeper into the hidden battles beneath the waves. On Exoplanet X, where sunlight never reaches, the food chain operates in ways that defy Earth's logic. Without photosynthesis to fuel the base of the ecosystem, life here relies on chemosynthesis, a process where microbes convert chemicals from hydrothermal vents into energy. These microbes become the foundation, supporting entire communities of creatures in a world where every meal is a matter of survival in the dark. At the top of this alien food chain, apex predators might rule with terrifying efficiency. Imagine sleek, bioluminescent hunters with bodies built for stealth, their glowing patterns shifting to mimic the ambient light of their prey. Some could possess elongated, needle-like jaws to snatch smaller organisms from the water, while others might use paralyzing toxins, delivered through glowing tendrils that lure victims into a deadly embrace. The absence of sunlight could have pushed these predators to evolve senses we can barely comprehend, perhaps detecting subtle changes in water pressure or electrical fields to track their next meal. But it's not all about brute force. Symbiotic relationships could thrive in these depths, turning cooperation into a survival strategy. Picture large, slow-moving creatures covered in colonies of bioluminescent bacteria, trading protection for light. These living lanterns might attract smaller organisms, which the host then filters from the water, a win-win in a world where energy is scarce. Even predators could form alliances, like packs of glowing hunters herding schools of prey into ambush zones, their coordinated light signals acting as a silent language of the hunt. Energy flows in strange loops here. With no plants to capture sunlight, the ecosystem depends on the constant churn of hydrothermal vents and decaying matter sinking from above. Scavengers might play a crucial role, recycling nutrients in a cycle of life and death that keeps the entire ocean alive. And in the darkest trenches, where pressure is crushing, life could take on bizarre forms, gelatinous filter feeders drifting through eternal night, or armored grazers scraping microbes off volcanic rock. One thing's certain, Exoplanet X's food chain is a high-stakes game, where every adaptation from bioluminescent lures to venomous spines has been honed by millions of years of evolutionary pressure. It's a reminder that even in the absence of sunlight, life finds a way, not just to exist, but to thrive in ways that challenge our understanding of nature itself. And as we peel back these layers, another question arises: what secrets lie buried even deeper beneath the ocean floor? Now, let's turn our attention to what lies beneath the ocean floor. On Exoplanet X, the mysteries don't stop at the water's surface, hidden beneath the crushing depths. Vast layers of subsurface ice, could play a critical role in shaping this alien world. Picture immense ice shelves stretching for hundreds of kilometers, acting like a second crust between the ocean and the planet's rocky core. These frozen barriers might trap pockets of liquid water, creating isolated habitats where life could thrive in ways we've only glimpsed on Earth, like in Antarctica's dark, buried lakes. The ice here isn't just a solid wall, it could be dynamic, shifting under pressure and heat from the planet's interior. Hydrothermal vents might melt pathways through it, forming networks of underwater caves where minerals and warmth sustain entire ecosystems. Imagine microbes clinging to these icy ceilings, or even complex organisms adapted to navigate the labyrinth of meltwater channels. Some creatures might use the ice as a shield, hiding from predators in its crevices, while others could rely on chemical reactions at the ice-water boundary to fuel their survival. What's fascinating is how this subsurface ice could act as a time capsule. Just as Earth's glaciers preserve ancient air bubbles, Exoplanet X's ice layers might hold clues to the planet's climatic past, or even evidence of extinct life. If the ice shelves periodically fracture, they could release trapped nutrients into the ocean, triggering blooms of organisms adapted to feast on these sudden bursts of resources. And then there's the possibility of life inside the ice itself. On Earth, scientists have found bacteria thriving in microscopic veins of liquid water within glaciers. On Exoplanet X, similar niches could host entire communities of extremophiles, their metabolisms slowed to a crawl by the cold, but never snuffed out. These resilient life forms might challenge our very definition of habitability, proving that even in a frozen, sunless prison, biology finds a way. As we ponder these icy depths, one thing becomes clear: Exoplanet X's subsurface layers could be as teeming with secrets as its ocean. The boundary between water and ice isn't just a line, it's a frontier, where the rules of life are rewritten in the silent, creeping flow of glaciers. And with that, we're left to wonder, what other surprises await in the unseen corners of this alien world? Now, shifting our gaze from the icy depths to the invisible forces at play, let's explore Exoplanet X's magnetic field, a silent guardian that could make or break life's chances on this ocean world. Unlike Earth, where our magnetic field is generated by the churning of molten iron in the outer core, Exoplanet X's field might arise from a different source. Given its global ocean, scientists suspect the planet's magnetic dynamo could be powered by electrically conductive salty water, circulating deep beneath the ice and rock. Imagine an ocean so vast and dynamic that its very motion creates a protective shield around the planet. This magnetic field isn't just a cosmic curiosity, it's a lifeline. Without it, Exoplanet X's atmosphere would be stripped away by the relentless stellar winds from its parent star, leaving the surface exposed to deadly cosmic radiation. Think of it like an umbrella in a storm. The field deflects charged particles, preserving the delicate balance of gases in the atmosphere and keeping the ocean beneath from boiling into space. For any life forms swimming in those dark waters, this invisible barrier could mean the difference between survival and oblivion. But here's the twist: Exoplanet X's magnetic field might not be as stable as Earth's. Tidal forces from its close orbit could cause fluctuations, creating temporary weak spots where radiation sneaks through. These gaps might trigger sudden bursts of mutation in marine life, accelerating evolution in ways we've never seen. Picture organisms with natural shielding bioelectric cells or mineral-rich shells evolving to cope with these cosmic intrusions. It's a reminder that on this alien world, Even the forces we can't see are shaping the story of life. And if the field is strong enough, it could do more than just protect. Auroras might dance beneath the ocean's surface, sparked by charged particles spiraling along magnetic lines. These underwater light shows could guide migratory creatures or even power bizarre, energy-harvesting ecosystems. Every flicker of this magnetic shield whispers clues about how life clings to existence in the universe's harshest corners. So while we marvel at Exoplanet X's watery surface and icy depths, let's not forget the unseen force holding it all together. The planet's magnetic field isn't just a scientific detail, it's the silent architect of a world where life, against all odds, might just be thriving. Now, let's turn our attention to the rhythms of Exoplanet X, the subtle yet powerful dance of seasons and climate that could shape its alien oceans. Unlike Earth, where our seasons are dictated by a modest axial tilt, this waterworld might experience something far more dramatic. If Exoplanet X has a significant tilt or an irregular orbit, its climate could swing between extremes, turning its global ocean into a swirling, ever-changing stage. Picture this during its equivalent of summer. Prolonged exposure to its stars' warmth might melt pockets of surface ice, creating temporary freshwater layers that alter ocean salinity. These shifts could trigger massive currents, redistributing heat and nutrients across the planet. Marine life here wouldn't just adapt to seasons, it might depend on them, migrating or hibernating in sync with these planetary cycles. But what if Exoplanet X's orbit is more elliptical, pulling it closer and farther from its star over time? The resulting temperature swings could be staggering. In the hot phase, evaporation might thicken the atmosphere, trapping even more heat and turning parts of the ocean into a steamy, turbulent soup. Then, as the planet swings away, a cold snap could lock the surface under a temporary ice shell, forcing life to retreat to the depths near hydrothermal vents. These climate swings wouldn't just affect temperature, they'd rewrite the rules of survival. Imagine organisms with flexible metabolisms, capable of switching between energy sources as conditions change. Or predators that emerge only during certain seasons, their life cycles timed to exploit fleeting bursts of prey. On Exoplanet X, evolution wouldn't just respond to the environment, it might race to keep up with it. And here's the kicker. If the planet's axial tilt wobbles unpredictably, like a spinning top losing balance, its seasons could become chaotic. Stable ecosystems might collapse, only for new ones to rise in their place. This constant upheaval could explain why life here evolved so fast. It's not just surviving change, it's thriving on it. So while Earth's seasons are a gentle ebb and flow, Exoplanet X's climate could be a roller coaster, with every twist and turn leaving its mark on the ocean's tapestry of life. Next, we'll dive into the fiery forces beneath the waves, the volcanoes and tectonic rifts that might be fueling this world's extraordinary biodiversity. Now, let's plunge deeper into the fiery heart of Exoplanet X, where the ocean floor isn't just a static landscape, it's a dynamic, ever-shifting stage for some of the most extreme geology in the cosmos. Beneath those endless waves, the planet's crust is alive with movement, cracked and stretched by tectonic forces far more intense than anything on Earth. Imagine vast underwater mountain ranges, their peaks hidden beneath miles of water, where magma erupts in slow-motion fountains, creating new seafloor in real time. These underwater volcanoes aren't just geological curiosities, they're lifelines. On a world without sunlight, hydrothermal vents act as oases, spewing mineral-rich plumes that feed entire ecosystems. The chemistry here is wild. Superheated water, packed with sulfur, iron, and other elements, mixes with the icy ocean, creating towering chimneys that might host colonies of alien microbes. And just like on Earth, these vents could be the cradle of life, offering both energy and shelter in the crushing darkness. But Exoplanet X takes it further. With tidal forces constantly flexing its crust, volcanic activity might be relentless, creating networks of vents that flicker on and off like cosmic streetlights. One day, a vent could collapse, only for another to burst open nearby, forcing life to adapt or migrate. This constant reshuffling of the seafloor could explain why evolution here is so rapid. Species that can't keep up with the changing terrain simply vanish, while others seize new opportunities. And then there's the pressure. At depths that would crush Earth's deepest submarines, these eruptions might look nothing like our fiery lava flows. Instead, picture a strange, slow-melting ice mixed with rock, oozing like syrup as it cools into bizarre formations. Some scientists even speculate that Exoplanet X's seafloor could host cryoval, Kanos volcanoes that erupt slushy ice instead of magma, reshaping the landscape in ways we've never seen. What's clear is this: the planet's geology isn't just a backdrop for life, it's the engine driving it. Every eruption, every tremor, every new vent is a chance for life to reinvent itself. Next, we'll ask the big question: could intelligence arise in these chaotic depths, or are we looking at a world forever ruled by its primal forces? Now, let's turn our attention to one of the most tantalizing questions about Exoplanet X. Could intelligent life exist in these dark, turbulent waters? It's a puzzle that pushes the boundaries of our imagination. On Earth, intelligence evolved in a world dominated by light, open spaces, and hands capable of manipulating tools. But here, the rules are entirely different. Picture a species navigating an ocean where sight is nearly useless, relying instead on sound, pressure changes, or even electrical signals to perceive their world. Communication might not involve speech as we know it. Perhaps clicks, vibrations, or bioluminescent pulses could form a complex language, and without solid ground, tool use would require entirely new adaptations. Imagine creatures with tentacles or flexible appendages crafting tools from volcanic rock or hardened vent minerals, all while floating in a weightless environment. The challenges are immense. Building shelters or technology underwater would demand materials that resist corrosion and pressure. Fire, a cornerstone of human advancement, is impossible here. So how would metallurgy or energy-intensive industries develop? Some scientists suggest that intelligence on Exoplanet X might revolve around manipulating chemistry rather than physics, harnessing the energy of hydrothermal vents or the planet's extreme gradients in temperature and salinity. Yet, nature is resourceful. If life here has thrived in chaos, why not intelligence? Perhaps cooperation is the key. Schools of organisms working together could achieve feats impossible for individuals, creating vast, interconnected networks of knowledge. Or maybe intelligence here is collective, with individual minds linking like nodes in a neural net, sharing thoughts across distances through chemical or electrical signals. The bigger question isn't just whether intelligence could arise, it's whether we'd even recognize it. Our definitions are rooted in Earth's history. On Exoplanet X, intelligence might look nothing like ours, thriving in ways we're only beginning to imagine. Next, we'll compare this alien ocean to Earth's own ancient past, searching for clues in our planet's deepest, most primordial memories. To understand the mysteries of Exoplanet X, let's take a journey back in time, to Earth's own turbulent beginnings. Our planet, 4 billion years ago, was a world of molten rock, violent volcanic eruptions, and oceans simmering under a toxic sky. The Hadean and Archean eons were periods of extreme conditions, not unlike what we see on exoplanet X today. But here's where the paths diverge and where things get fascinating. Early Earth's oceans were hot, acidic, and bombarded by ultraviolet radiation, yet life emerged in these harsh waters, likely around hydrothermal vents. Exoplanet X's oceans, while also vent-rich, are shielded by a thick atmosphere and bathed in the gentler light of a cooler star. This difference in energy sources could have steered evolution down an entirely new path. On Earth, photosynthesis eventually transformed the planet, flooding the atmosphere with oxygen and paving the way for complex life. But on exoplanet X, where sunlight barely penetrates the ocean's surface, life may have skipped photosynthesis altogether, relying instead on chemosynthesis, a process fueled by chemicals spewing from hydrothermal vents. Then there's the question of time. Earth took hundreds of millions of years to develop even the simplest cells. Exoplanet X, with its faster orbital cycles and intense tidal forces, might have accelerated evolution, compressing timelines dramatically. Imagine a world where life didn't just emerge, it sprinted forward, adapting to rapid shifts in temperature, chemistry, and pressure. The most striking parallel, though, lies in the unknown. Just as Earth's early life left few traces, exoplanet X's biological history might be hidden in its depths, waiting to be deciphered. Could its oceans hold clues to life's origins that Earth's rocks have long since erased? The answer might rewrite our understanding of how life begins and where it can thrive. Now, let's shift our gaze to the technological hurdles of exploring this alien world and the daring missions that could one day unveil its secrets. Exploring exoplanet X is no small feat, and the challenges we face are as vast as its alien oceans. First, there's the sheer distance. This waterworld orbits a star hundreds of light-years away, making even the most advanced telescopes struggle to capture more than blurry glimpses. Current technology can detect its atmosphere and surface composition, but peering into its deep, dark oceans, that's like trying to study a swimming pool from space with a pair of binoculars. Then there's the problem of instrumentation. Our probes and rovers are built for rocky planets like Mars, not a planet-wide ocean with crushing pressures and corrosive chemistry. Traditional cameras and sensors would fail in minutes under those extreme conditions. Even communication becomes a nightmare, sending signals through hundreds of kilometers of water, and an atmosphere thick with storms is a hurdle we've never tackled before. But here's where human ingenuity shines. Scientists are already dreaming up solutions, like autonomous robotic submarines designed to withstand exoplanet X's brutal environment. These wouldn't be your average underwater drones, they'd need reinforced hulls, advanced AI to navigate uncharted depths, and maybe even biomimetic designs inspired by Earth's deep-sea creatures. Imagine a fleet of mechanical squid darting through hydrothermal vents, collecting samples where no human-made device has gone before. Another possibility. Deploying floating observatories on the planet's surface, equipped with sonar and chemical sniffers to map the ocean from above, or perhaps nanoscale probes, tiny enough to drift with the currents, broadcasting data back to orbiters. The key is redundancy, sending not one, but dozens of missions, knowing many might fail in such an unforgiving world. And let's not forget the role of AI. Machine learning could analyze real-time data to adapt missions on the fly, pinpointing hotspots for life or avoiding dangerous terrain. Pair that with next-generation telescopes, like the successors to James Webb, and we might finally crack Exoplanet X's mysteries without ever leaving Earth's orbit. Of course, every breakthrough raises new questions. How do we power these devices in an ocean with no sunlight? Could they contaminate an alien ecosystem? The road ahead is daunting, but the potential rewards, a glimpse into evolution's wildest experiments, are worth every obstacle. Now, let's turn to the ethical dilemmas lurking beneath the surface. Should we even interfere with a world that's thrived without us for billions of years? But before we dive deeper into the technology, we must pause and ask ourselves a difficult question. What right do we have to interfere with a world that has existed perfectly fine without us for billions of years? This isn't just about scientific curiosity, it's about responsibility. The moment we send probes into Exoplanet X's oceans, we risk introducing Earth microbes that could contaminate an alien ecosystem. Even our cleanest spacecraft carry trace bacteria, and in an environment as isolated as this, those microbes might thrive, outcompeting native life before we even discover it. Then there's the opposite concern. What if Exoplanet X's chemistry is hostile to our probes? Acidic waters or exotic microbes could corrode equipment, turning our technology into toxic debris scattered across the ocean floor. We could accidentally trigger a chain reaction, altering water chemistry, disrupting food chains, or even wiping out species we never knew existed. Some argue that exploration is worth these risks. After all, studying Exoplanet X could revolutionize our understanding of life itself, but others counter that we should observe from a distance, using telescopes and passive sensors to minimize our footprint. There's precedent for this. NASA, planetary protection protocols strictly limit contamination risks for Mars and Europa. Should Exoplanet X get the same safeguards, even though it's light years away? And what about active signals? If we detect possible signs of intelligence, do we announce our presence? The consequences are unpredictable. A civilization advanced enough to receive our messages might see us as a threat, or worse, prey. On the other hand, staying silent means missing a chance to connect with another thinking species, something humanity has dreamed of for centuries. Perhaps the answer lies in balance. We could explore cautiously, prioritizing non-invasive methods until we fully grasp the stakes, or we might establish international agreements, much like the Antarctic Treaty, to govern how we interact with alien biospheres. One thing's certain: the choices we make now will echo across the stars, setting a precedent for how humanity treats life beyond our world. Now, let's shift our gaze from ethics to imagination. How has this distant ocean world already inspired stories right here on Earth? Turning our attention closer to home, Exoplanet X has already made waves in human creativity long before we confirmed its existence. Science fiction writers have dreamed up ocean worlds for decades, but this distant planet brings those fantasies into startling reality. Think of classics like Solaris, where a sentient ocean challenges human understanding, or the recent film The Abyss, which imagined intelligent life thriving in crushing deep-sea pressures. These stories now feel less like fiction and more like eerie premonitions. Artists, too, have been captivated by the possibilities. Digital painters imagine Exoplanet X's bioluminescent depths, creating swirling landscapes where alien jellyfish pulse with light and towering hydrothermal vents spew minerals like underwater geysers. These visuals don't just spark wonder, they shape how the public envisions alien life, fueling support for real-world exploration. Even video games have joined the fascination. Titles like Subnautica and Soma drop players into alien oceans teeming with strange creatures, subtly preparing us for the day we might encounter the real thing. These interactive experiences make the abstract tangible, letting millions explore an exoplanet X-like world from their living rooms. But here's the twist: this cultural fascination isn't just entertainment. It drives scientific progress. When a sci-fi novel accurately predicts extremophiles or tidal-locked ecosystems, researchers take note. Public excitement generated by these stories often translates into funding for telescopes and deep-sea probe research, creating a feedback loop between imagination and discovery. Perhaps most intriguing is how Exoplanet X blurs the line between scientist and artist. Astrobiologists now consult with sci-fi authors, exchanging ideas about plausible alien ecosystems. Meanwhile, filmmakers use real exoplanet data to design their alien worlds, making the fiction feel unnervingly authentic. This collaboration reminds us that to understand the universe, we need both logic and creativity, the rigor of science and the boldness of storytelling. Now, let's confront one of astronomy's biggest puzzles. If life thrives on Exoplanet X, why haven't we heard from it? The answer might lie in the Fermi paradox. But here's something to ponder. If Exoplanet X is teeming with life, why does the universe seem so silent? This brings us face to face with the Fermi paradox, the puzzling contradiction between the high probability of alien civilizations and the complete lack of evidence for them. Exoplanet X might hold clues to this cosmic mystery. One possibility is sheer isolation. Imagine an intelligent species evolving in that endless ocean, surrounded by crushing pressures and perpetual darkness. Even if they developed technology, their environment could make space travel nearly impossible, building rockets underwater, communicating through dense, swirling currents. These aren't just challenges, they might be insurmountable barriers. Then there's the extreme environment itself. Life on Exoplanet X could be so different from ours that their technology leaves no trace we'd recognize. What if their version of radio waves travels through water in ways we can't detect? Or if their entire civilization thrives around hydrothermal vents, with no need to explore beyond their abyssal plains? Another angle is time. Earth has been around for 4.5 billion years, yet human civilization is a blink in cosmic terms. Exoplanet X's inhabitants might have risen and fallen millions of years ago, their signals lost to the void. Or perhaps they're still in their microbial stage, with intelligence yet to emerge. But here's the most intriguing thought. What if we're looking at the Fermi paradox all wrong? Instead of asking why we haven't heard from them, maybe we should ask, are we listening the right way? Our searches focus on radio signals and laser pulses, but Exoplanet X's life could communicate through chemical trails, pressure waves, or even bioluminescent flashes. Our tools aren't designed to catch those whispers. This paradox forces us to rethink not just Exoplanet X, but our entire approach to the cosmos. The silence isn't necessarily emptiness. It might be a sign we're only beginning to understand the vast, strange possibilities of life. And with that, let's turn to the next chapter: how future missions could finally crack this mystery wide open. Now, let's turn our gaze to the future, because the next wave of missions could bring us closer than ever to unraveling Exoplanet X's mysteries. Imagine telescopes so advanced they can peer into the chemistry of distant oceans, or probes designed to survive the crushing depths of alien seas. The tools we're building today might finally bridge the gap between speculation and discovery. Take, for example, the upcoming Habitable Worlds Observatory, set to launch in the next decade. This powerhouse telescope will specialize in analyzing the atmospheres of exoplanets, hunting for biosignatures like oxygen, methane, or even industrial pollutants. If Exoplanet X has a biosphere, this observatory could spot the chemical fingerprints of life from light years away. But why stop at observation? Breakthrough initiatives like Project Starlight aim to send tiny, laser-propelled probes to nearby star systems. While Exoplanet X might be too distant for this mission, the technology it pioneers, nano-probes that can travel at a fraction of light speed, could one day deliver sensors directly into its ocean. Picture microscopic devices drifting through alien currents, relaying data back to Earth over centuries. Then there's the tantalizing idea of cryobots, robotic submarines built to melt through ice shells on moons like Europa or Enceladus. Adapt that tech for Exoplanet X, and you've got a machine capable of plunging into its abyss, withstanding pressures that would crush conventional subs. These bots could map hydrothermal vents, sample microbial life, or even stumble upon structures built by intelligent beings. Of course, the biggest challenge remains distance. Exoplanet X orbits a star far beyond our reach with current propulsion, but innovations like nuclear thermal rockets or antimatter drives, still in early stages, could one day slash travel times dramatically. Imagine a mission arriving in decades instead of millennia, opening a window into that watery world. What might these missions find? Perhaps vast forests of tube worms thriving near vents, or schools of bioluminescent creatures flashing in the dark. Maybe even ruins of a civilization that never left its ocean cradle. Every discovery would rewrite our understanding of life's potential. The truth is, we're on the brink of a new era. With each technological leap, Exoplanet X shifts from a blur in our telescopes to a world waiting to be explored. And when that day comes, the universe might finally break its silence. Now, let's consider how the secrets of Exoplanet X might echo back to our own world. Studying this distant ocean planet isn't just about satisfying curiosity. It could hold vital lessons for Earth's survival. Imagine unlocking strategies for climate resilience by observing how Exoplanet X's thick atmosphere traps heat or distributes ocean currents. Its extreme conditions might reveal how life adapts to rapid environmental shifts, offering clues to protect our own ecosystems as Earth's climate changes. Then there's the puzzle of ocean conservation. If Exoplanet X's global sea harbors life thriving under high pressure and darkness, it could reshape how we view Earth's deep-sea habitats. We might discover new extremophiles here that mirror those on Exoplanet X, inspiring better ways to safeguard our ocean's unexplored depths. After all, less than 20% of Earth's seas have been mapped. What if the key to preserving them lies in studying an alien world? And let's not forget the hunt for life closer to home. Exoplanet X's hydrothermal vents, teeming with potential organisms, could guide our search on icy moons like Europa or Enceladus. If life flourishes in its abyss without sunlight, why couldn't the same happen beneath Europa's frozen crust? Missions to these moons might borrow detection methods first imagined for Exoplanet X, turning theory into reality. Perhaps most profound is the perspective shift. Discovering life on Exoplanet X would prove that biology isn't a fluke of Earth, but a cosmic inevitability. That realization could unite humanity in stewardship of our planet, knowing how rare and precious a living world truly is. The more we learn from Exoplanet X, the better we might care for our own blue marble, ensuring it remains a cradle for life, not a cautionary tale. As we stand on the brink of these discoveries, one thing is clear: the future of Earth and the mysteries of Exoplanet X are more connected than we ever imagined. As we wrap up this journey through the mysteries of Exoplanet X, let's take a moment to reflect on what makes this distant ocean world so extraordinary. A planet almost entirely covered by deep, global seas, where life may have evolved at a pace that leaves Earth in the shadows. Its thick atmosphere shields it from cosmic threats, while tidal forces churn its waters into a dynamic, ever-changing environment. Hydrothermal vents, possibly teeming with alien life, could rewrite the rules of biology as we know them. And let's not forget the haunting beauty of bioluminescent ecosystems, lighting up the eternal darkness of its abyss. Exoplanet X isn't just another world, it's a mirror held up to our own planet, challenging everything we thought we knew about life's possibilities. It forces us to ask, if life can thrive in such extreme conditions out there, what does that mean for the undiscovered corners of our own oceans, or for the icy moons right here in our solar system? The answers could redefine humanity's place in the cosmos, but the story doesn't end here. Every new discovery, every mission to the stars, brings us closer to unlocking these secrets. That's why supporting space exploration matters. It's not just about satisfying curiosity, but about expanding the horizons of human knowledge. Who knows what other wonders are waiting to be found? So what do you think? Could Exoplanet X be home to intelligent life, or are we looking at a world of microbial marvels? Drop your theories in the comments below. I'd love to hear your ideas. And if you enjoyed this deep dive into the unknown, don't forget to like, subscribe, and hit that notification bell so you never miss an adventure into the cosmos. The universe is full of mysteries, and together, we'll keep exploring them one discovery at a time. Thanks for watching, and stay curious.